recording now. So yeah, so it's a 115 slides, but we're not going to cover everything. We're only going to cover the first half, really, because that's the only thing that's going to be on your exam 3. So basically, I guess we'll get started. Now, last class on Monday, we learned about Lewis structures. We learned about electronegativity, polarity, different kinds of the electron properties of chemical bonding, right? So where are the electrons? Are they pulled more towards one or the other? Single bonds, double bonds, triple bonds, and the amount of pairs of electrons, basically electron behavior. Today, we're going to be learning a little bit more about that and how the electron behavior and the positioning affects the shape of the molecule. So that's the main takeaway from today's class, is the shape of the molecule. And there's 2 types of shape, right? So we're going to be learning about the molecular geometry and the electron geometry, and they are both actually different. So one of them is easier than the other, but they both describe different phenomena and go through different concepts. So also we'll be talking about how the shape of the molecule affects its properties. So reactivity, polarity. So we learned about how to determine if a molecule was polar, or really if a bond was polar. We didn't really talk about if a molecule was polar and what makes a molecule polar. It's the same concept with you need a difference in electronegativity, or you need one atom to pull the electrons more towards it than the other atom to create partial charges. That concept is still true. But if you have a molecule, such as, let's say, BF3, that has multiple bonds, let's say it has 3 BF bonds, is this molecule polar? And the answer is actually no, it's nonpolar, even though the bonds between B and F are heavily polar, because fluorine, is the most electronegative atom, and boron is not that electronegative. But the idea is, for a molecule, if you have symmetry, then you will not have polarity most of the time. So in actuality, this picture is more realistic, where the BF bonds are evenly spaced 120 degrees away from each other, so that they would create an equal pull in every direction of the electron. The fluorines will pull the electrons equally in every direction. So that will make the molecule nonpolar, even though the bonds are polar. So we're going to be talking about that, and also we're going to be talking about the different shapes. So we'll get into it. And the shapes are called the VSEPR theory. So VSEPR stands for valence shell electron pair repulsion theory. It sounds more complicated than it is. But it basically, that name is very accurate. So we're going to be learning about valence electron or valence shell electron pair repulsion. So there are many electron pairs in molecules, as we saw with the Lewis structures, that there are bonds and there is electron pairs that are lone pairs. These lone pairs affect the bonding geometry, meaning they have repulsion. So that's why it's called the electron pair repulsion theory. So we'll examine that. Now, there's the 2 main geometries. Here they are. So here's definitions: electron geometry and molecular. We'll learn both of them in the same chart, and I'll annotate the chart as we go along. So electron geometry, it takes into account the number of electron-containing groups on the central atom. So something we do need to define is electron-containing groups. So what that means basically is a lone pair of electrons is an electron-containing group. A single bond is an electron-containing group. A double bond is an electron-containing group, and a triple bond is one as well. Meaning any group that is, I like to call them, so we're going to talk about steric number, but I like to call them limbs off the central atom, meaning, I'll explain that in a second. But yeah, so then you have the molecular geometry. So the molecular geometry takes into account the effect of the lone pair electrons on the shape of the molecule. So basically, for molecular geometry, we only consider the bonds. So the bonds to other atoms off of the central atom as making the geometry. Whereas electron geometry, we take every electron-containing group, and we call those kind of limbs, or that contributes to the steric number. Whereas molecular geometry, we do we examine the effect of the lone pair electrons, if there are any, on the shape of the molecule based on just its bonds. So hold on, let me get my my pad and plug it in. So I can start to write stuff. All right. All right. So here is this thing called steric number that it kind of determines the electron groups. So steric number definition is the bonding pair of electrons plus the lone pair of electrons. So I don't like that. I still don't like that definition perfectly. It's not a perfect definition, but an easy way to describe it, steric number. Wait, what just happened? I'm going to have to close this and then reopen it. Because the pen only detects, the pen only works when it is opened. Where is it? There we go. Okay, cool. Let's see. There we go. All right, cool. So the steric number is basically, I call it the number of things, the number of limbs coming off of the central atom. So in this molecule, NO2, you have the central atom's nitrogen. There is one lone pair of electrons, one single bond, and one double bond. Therefore, the steric number is 3. So there's 3 electron groups. So this is what I mean by electron-containing groups. It could be either one of these things, or it could even be a triple bond. So it's not that the double bond is only one electron group, not 2, because it's a singular entity that holds a number of electrons, just like the single bond and just like the lone pair. So they all count equally as contributing to the steric number. And then the way that I like to describe it is the limbs off a central atom. So if you want to take, let's say, nitrogen, you can kind of view it like this. We'll do the same nitrogen. And you could view it as this is a lone pair. This is one limb. This is another limb. So it's kind of like different electron clouds, because the way electrons behave, they're not stationary. Even electrons in bonds are moving around a lot. So it's kind of like an electron cloud. That's why the electron geometry is important. It describes where or how many electron clouds there are and how that contributes to the bonding how it would contribute to the reactivity and bonding to other elements. So, yeah, that's what the steric number is. And that's why it's important. So those are your limbs. Yeah.
Can you go over the steric number for N2? Because I believe that was on the homework and I kept getting it wrong.
Okay, so N2 is going to be a triple bond like that. And it's going to have like that. So that's N2. So the steric number would be 2.
Why wouldn't it be 3? Because it's per nitrogen?
Yes. So in a that's a really good question. So in a molecule which has no central atom, you just, let's say if it's N2, you just pick one of them. They're both the same. So what would happen is the steric number, or did they say the steric number of nitrogen in N2 or just N2?
They just said steric number of, I think it was nitrogen in N2.
Right. If it's nitrogen in N2, then it would be 2, because you have one electron group, and then the triple bond counts as the second electron group.
Okay.
If it says the steric number for the entire molecule, which is also possible, then it would be 3.
Okay.
Because this is a small enough molecule where the steric number of it would still be relevant. So, yeah, good question. Okay, so now we're going to get to the big chart. So this is the main takeaway of today's class, is understanding this big chart. Now, we'll get into it. I'll talk about what it is first. So you have different examples of bonding order. And on the left side here, you have the steric number. So steric number is 2, 3, 4, 5, or 6, which means the limbs, which means how many electron groups are coming off of the central atom. And you notice as you increase your steric number, there's different combinations of bonding and non-bonding electrons. So I'll say that again. As you increase your steric number, there's different combinations, non-bonding and bonding electrons. Now, those combinations are called your molecular geometries. So that's why this chart, all of these names are molecular geometries. If you want to talk about electron geometry, the electron geometry is the same for every steric number. And I'm going to write these down. I'll write these over here. So I'll write down EG, electron geometry. So for everything that has a steric number of 2, there are other options actually. You can have, just like nitrogen in that example, you can have this, right? Technically, this is a steric number of 2 because it has a lone pair and a triple bond. So anything with a steric number of 2, the electron geometry would be linear. Anything with a steric number of 3, electron geometry would be trigonal planar. And you notice I'm going to write down the electron geometries for all these steric numbers, and they're going to be the same as when there is no lone pairs. So for 4 steric number, it's going to be tetrahedral. Tetrahedral is one word. I just don't have room. And then for 5, it's going to be trigonal bipyramid. Sometimes you call it bipyramidal or trigonal bipyramid. That's fine. And then for 6, it's going to be octahedral. It's weird how it's octahedral, not hexahedral or something, but it's octahedral. All right. So now we know that. So basically what that means is every time you have a steric number of 4, it's going to be tetrahedral, no matter what the combination of bonding or lone pair electrons there are. That's pretty easy, right? I mean, you just count up what the steric number is, which we already know how to do. For example, let's say you have a carbon, 1, 2, like that. So the steric number would be 1, 2, 3. And then you would see, oh, what's 3? Trigonal planar. That means the electron geometry for this atom would be trigonal planar. So you would just do that. Any questions on that? Okay, cool. So now the harder part, which is the molecular geometry. That's molecular geometry. Now, the molecular geometry is kind of like the electron geometry, but it actually takes into the account the effect of those lone pair electrons. And it doesn't make them equal to the lone pair electrons in terms of the shape. So that's why we call it electron geometry, meaning just the electron groups. Molecular is the shape of the molecule itself. So let's start with the basic ones where you have the molecular geometry for if you have 2 bonds, it is linear, right? 2 bonds and no lone pairs, it's called linear. And that makes sense because your electron groups that are bonded, so I'll say something first. So if you have a non-bonding group of electrons, meaning a lone pair, they are more reactive than electrons that are in a bond. And that makes sense, right? Because bonds form to minimize the energy between atoms. So the electrons are in a lower energy state and a less reactive state when they are bound in a single, double, or triple bond when compared to a lone pair electron. This is important because, I mean, either way, your bonded electrons are going to try to repel each other because they're both electrons. They're not happy next to each other. But the reason why I mention that is because when we introduce the lone pairs, they're going to create a greater repulsion effect than a bonded pair. So whereas a normal bonded pair, they would try to get as far away from another bonded pair as possible. So here you have 2 electrons in this bond, and there's 2 in this bond. They don't like each other anyway. Even though they're kind of stable, they don't like each other. So they're going to balance out one on either side of the atom, of the central atom, 180 degrees away. So the degrees are important too, to have an understanding of, I mean, once you get down here, it gets kind of complicated, but you see that it's not, I mean, it makes sense once I explain it. that, oh, it makes sense that that's less than 109 because there's more repulsion, stuff like that. So basically, there's linear. So they're 180 degrees apart because the electrons are repelling each other in the bond. The bonded electrons are repelling each other. And then for molecular geometry, this would have none because it's just, there's no other atoms it's attached to. So yeah, that's just an example for electron geometry. Okay, moving on. So, and also feel free to stop me, even if I'm on a roll, just stop me. To answer the question. Yeah.
How many of these should we memorize?
Good question. So linear, the steric numbers 1 through 5 are important. So here's what I'll do. I'll underline the ones in gray that are not the most essential. So the sawhorse or seesaw, whatever you want to call it, T-shape, this kind of linear, T-shape, square planar is not, yeah, these are, yeah, those are important, and then linear. So once you get down here, like some of them are like, you're probably never going to see them or maybe once in a while, but not essential to know those. Every other one is pretty important. Okay, cool. Good question. All right, so now let's go to steric number 3 for molecular geometry, and I'll explain why. So first you have no lone pairs, and also on the top, on the x-axis here, if you want to call it that, you have the number of lone pairs. So no lone pairs. The molecular geometry is going to be the same as the electron geometry. That's a key thing. So electron geometry is the same as the molecular when there aren't any lone pairs to create any additional repulsion. So here you have, they are perfectly 120 degrees away because, you know, 120 times 3 is 360, and it's in a circle. So, and also it's trigonal planar, meaning it's on one plane. So that makes sense. Then what's going to happen is when you replace one of those bonded electrons or bonded groups with a non-bonded group, what's going to happen is that bonded group, that unbonded group, is going to have a higher repulsion effect than a bonded would, just like I mentioned. So it'll create repulsion of the two bonds, and it'll kind of squeeze them together like that. And what that does is it minimizes the angle where before it was 180, now it's going to be less than 180. How much less? It depends. So there's a wide range, and all very close, maybe 110, maybe it's 95. It depends on what the atoms are. So just know that it's less than 110. Or sorry, 120. And it should make sense conceptually why this is true because of the repulsion. So any questions on that? So I don't like to stress memorizing, but just an understanding of why that is. And what we're going to call this shape is we're going to call it bent. Angular, nobody calls it angular. So I'm going to erase that term. So we call it bent. And the reason why it's bent is, you know, it's bent. So because of the pairs. Okay. And we're also going to see bent again. And we're going to see that in water. So this is what water would look like. But we'll get to there. So any questions on steric number 3, where you have 2 possible molecular geometries? You have trigonal planar when there is no lone pairs, and bent when there is 1 lone pair because it pushes the other 2. Okay. Going on to steric number 4. The basic no lone pair configuration shape is tetrahedral. So tetrahedral is when you have either 4 electron groups when you're talking about electron geometry, so that's all of these. When you're talking about molecular geometry, it's only when you have 4 bonded groups. So a perfect example of tetrahedral for molecular would be methane. So you'd have CH4.
Professor?
Yes.
Is there any way you could change the color of your cursor?
Yes. What color?
Any
Green?
color that's not white.
Wait, it's not white. It's red.
It's white for me.
Oh.
The cursor itself is white. You're drawing red.
Oh. Huh.
Because like when you say something like, if you look at these and like you're moving your cursor around something.
Is it black now, the cursor?
It's probably not because I can't.
Oh, you can't see. Yeah. So I'm hovering around The 109.
Yep, there you go. It's still white.
Oh,
Still
damn
white.
it. How do I? No.
It was just like a little confusing.
Is
There
it
you go.
highlighter
That's
now?
there. That you can see what you're.
This is
pointing at
yellow now?
Yeah.
Okay, cool. All right, I guess I'll do that. Yeah. All right. Cool. Thanks.
All
right. So this is tetrahedral right here. So for methane, I'll go over here. So methane on the right side over where I'm drawing right now. So that's methane, and that is tetrahedral for molecular geometry. And it has no lone pairs like this one. Then what happens, and that's 109. The angle is 109. It's actually 109.5. So that's an important angle to know. And the reason why it's 109 and it's not, you would think it's 90, right? Because 90 times 4 is 360. But keep in mind, tetrahedral is in a 3-dimensional area. So if you were to space 4 things apart in a 3-dimensional area, you would get a tetrahedral shape, and the angle between them would be 109.5. So that's tetrahedral. Then what happens when we look to the right here in trigonal pyramidal, or they call it trigonal pyramid, you can call it trigonal pyramidal. So trigonal pyramidal, if you take away one of the electron groups that is bonded, replace it with a non-bonding group, a lone pair group, you get repulsion. So you get this repulsion. And what that does is it squeezes the 3 electron groups, squeezes them together to create kind of like a tripod, right? So you imagine all these 3 going down, and it'll create like a tripod. That's exactly what you call it. You call it trigonal pyramidal. In other words, a tripod. And the angle between the 3 would be less than 109, because where there was no electron groups, it was 109. Now the squeezing them together makes it less than 109. A perfect example of a trigonal pyramidal is NH3. So I'll draw it on the right side over here, NH3, where you have these electron groups would push like that. And it's always a common thing to compare methane and NH3 and ammonia, because they are both tetrahedral with respect to electron geometry, right? Because you have methane's 1, 2, 3, 4, and ammonia, which is one lone pair, 2, 3, 4 pairs. So you would have tetrahedral electron geometry. But for molecular, that's where it would differ. Methane would still be tetrahedral, and NH3 would be trigonal pyramidal, or trigonal pyramid, or a tripod. Okay, any questions about that? All right, I think tetrahedrals, these 3 are the most important because you see them in a lot of our key molecules. So let's talk about the next one is where you replace. The next one is where you replace the second bonded atom with an electron pair. So now you have 2 electron pairs, and think about them, they're not next to each other. So you would think that's what these lines mean, that the solid line, not the solid one, means that they're more, it's forward, and the hashed one means it's backwards. So think about them as kind of like a V, right? And they're kind of like flipped. They're 90 degrees. They're facing, one's facing directly towards you, one's facing directly away. Meanwhile, these 2 X atoms are facing to the left and to the right. So it creates like a staggered pattern. So that's in order to make the electrons furthest away from each other. Now, these, even though they're furthest away from each other, these lone pairs on the top are still going to create a repulsion effect to make the angle a lot less than 109. It might be this time in the 70s, in the 80s, obviously depending on what the atom or what the molecule is. So yeah, and a perfect example of this, I'll draw it on the right side here, is water. So you have oxygen, hydrogen, hydrogen, 2 lone pairs of electrons on oxygen, and they're going to repel the bonds and kind of push them in more. So that's what you have. This is called bent. And you saw bent already, where it was observed when you have a steric number of 3 in this configuration where you have 2 bonds and 1 non-bonded. The same thing happens when you have two bonded, but the repulsion force is going to be a little bit stronger. Where this one was less than 120, this one's going to be less than a lot less than 109. So yeah. Any questions on Steric number 4 for the molecular geometries? There are 3 of them. So the easiest way to figure out this is, if you are familiar with this chart, write the Lewis structure first. If you count up your Steric number, you can easily figure out your electron geometry and then see, all right, out of those, how many are lone pairs? And then do they push down? I mean, they're going to push down. So they, how many lone pairs are there and how many bonded pairs? And then you can see what pushes down. And you can see your molecular geometry. Okay, 2 more. So the next one is trigonal bipyramidal. So what that means is kind of like a pyramid. It's kind of like a pyramid, but it has 2 tops. That's why it's called, or it's like a tripod with 2 tops. That's the way you think about it. So kind of like, imagine that these 3 on the top left here, these 3 X's were a tripod. So one of them's going in, one of them's going out, and one of them's going straight. And you kind of rest it on a tripod. Then you have 2 other branches coming out of the tripod in opposite directions like this. That's what it means. Trigonal pyramidal, bipyramidal, sorry. So for the electron geometry, they're all trigonal bipyramidal. When you have no electron pairs, it's still trigonal bipyramidal for the molecular geometry. And then you can see what happens when you increase the amount of pairs, decrease the amount of bonds. If you make it 1 pair, they call it this sawhorse or seesaw, which basically means that these two atoms are going to be staggered in one direction and kind of like a seesaw, and then you have one on each side. And it'll kind of create like a rocking. It'll kind of rock. If you sat it down, it would be a lot easier if I had the molecules, like the molecular models, to show you, but you can imagine it would like rock. And the reason why is the same thing as before. You have the electron repulsion. So it would do that. And don't really worry about the angles for these, because, I mean, you should be able to deduce the angles. You know that there's 2 types for Steric number 5. There's either a 120 or a 90. If you add groups, lone pair groups, it just makes it less than 90, less than 120, and then when you add more groups, you'll see what it does. So next is T-shaped. So this is when you have 2 lone pairs, and they're going to push down the 3 bonds even more, like that. So, and it'll create like a T. It'll kind of be like taking a trigonal planar and putting 2 electron groups here, which pushes them together. And it'll still make a T, but it'll kind of push them together in a trigonal planar. So that's that. Yeah. Okay. Next one is a little bit different, because now you are only down to 2 bonded pairs and 3 non-bonded pairs. So what happens is, you notice a transition that once you add 2 non-bonding or 2 lone pairs of electrons, that's the maximum number of lone pair electrons that can be on one side of a molecule. One can go away from you, one can go towards you. When you add more than that, so in this molecule, get my highlighter again. So in this molecule, the linear molecule, you have 3. You're adding this one. When you add that one, there's no room for it on the left side. You have the one going away and the one going towards you. So what happens is there's no choice by energetic favorability, but it has to go on the right side, on the other side of the molecule. What this does is it creates a repulsion in the other direction. So I kind of figure this as these electrons are going towards us, these are going away from us, and this one's going directly this way. So it'll kind of create like a, think about it as the electron group, the lone pair electron groups are creating a trigonal planar arrangement like this, like around. I wish I was in 3 dimensions, but and I wish I could use my hands to talk about this. But hopefully you see what I'm saying. They're kind of, the electrons are creating like a force field, like a barrier that's going in circles really fast. That is going into the page. It's horizontal. So if that's the case, the only way that the electron groups that are bonded, or the atoms that are bonded, could arrange is if one is on the extreme one end and the other is on the other extreme end, making a 180 or linear arrangement. So you can have linear in multiple cases where you have just 2 bonded electrons or bonded pairs, and then you could have 2 bonded pairs and 3 lone pairs, and you can even have 2 bonded pairs and 4 lone pairs, which you'll see next. All right, so those are getting a little bit more complicated, but is there any questions on them? No? Okay, cool. All right, next is octahedral. So you would think that means 8, but it doesn't. It means 6. I don't know who made that up. But octahedral, you have multiple cases of octahedral electron geometry, but only one case of octahedral electron geometry. And a very common molecule with that, which you might see, is SF6. So also for trigonal bipyramidal, you might see PF5. Nope. Here you go. PF5. That's a common one. And they exceed the octet rule, but they are still stable because they don't have any formal charges. So, and you can figure that out. You can do the math. Okay. So octahedral is you have 6 bonded groups. So SF6 is a perfect example of that. And the degrees, since they're 3-dimensional space, the angle between all of them are 90 degrees, because 90 times 6 is 360. Well, it's not y, but I mean, if you arrange 6 things in 3-dimensional space, the angle between them is 90. So that's just the way it works. Then what's going to happen is, as you increase, you get rid of one bonded pair, put a lone pair, it's going to create the repulsion again, the VSEPR. So this will repel, and you'll create what we call a square pyramid. So you can kind of think about it as a pyramid, well, kind of like a normal pyramid, meaning the bottom of it is a square and the top of it is just the top. So you kind of make like a pyramid like that. Like that. It's a pretty good pyramid. Yeah. So that's what we mean by square pyramid. And the electrons are pushing it. The lone pair electrons are pushing the bonds in that direction to make that shape. Then what will happen is if you add another electron group, it'll create square planar. So this means you're getting rid of this one, making another electron group. You're getting rid of this one, creating another electron group. And those electron groups are going to behave and be on the opposite ends of one another, thus forcing the atoms to be, or the bonded atoms to be, in the middle. So like kind of like one will be facing, 2 will be facing that way and into the page, 2 will be facing towards us, and you'll have a square planar. So it'll be on a square, kind of like trigonal planar, but square planar. And the electrons are forcing it in that space. Then you're going to have 3 bonded pairs. 3 non-bonded electron pairs. If you have that, well, it's what we call T-shaped, which means that they arrange in this way. I mean, you have 2 on one end, and it's going to be 3. The third one's going to be going that way. And then the atoms have nowhere to go besides being in a T shape. So this X, this one right here, is going to be facing towards us, and the other one's going to be facing away from us. Or the other one's going to be facing on the plane. So it'll create kind of like a T. So, yeah. Any questions about that? That one's not really that important. You might not see it ever. It's rare, but it exists. Then you have linear again. This one actually you do see. XF2, I think, is one of them. But, and you can see why the ones I did underline in gray that you may not encounter that much, they all exceed the octet rule. So that's part of the reason why they're not that common, because there aren't many molecules that exceed the octet rule that are stable with these configurations, but you still might see it. I mean, think about it. All of these, everything from steric number 5 and 6 exceed the octet rule. Some of them are stable though, like trigonal bipyramidal. There's multiple molecules that are stable. Same thing with octahedral, even square pyramid and square planar. But everything else, it's kind of, there's not many molecules that exhibit that arrangement, that molecular geometry, while still being stable. So the last one is linear, where you have 2 lone pairs in one direction, 2 lone pairs in the other direction, and that kind of makes a force field, kind of like our linear over here. Same kind of force field, but you have 1 more pair of electrons. And that creates a stronger force field, which kind of holds the atoms in place at 180 degrees. So I'll erase these circles in case you want to look at it. But yeah, so that's basically it. Any questions? Ask questions. So I know it's a lot, but the following slides kind of break it down one by one, but we already did talk about it, and there's not really much to add. So yeah, this is, I don't know, I'm not sure what minute of the video this is, but if you want to, when you're watching on YouTube, if you actually do that and watch the lectures again, this first part is like the most important of the chapter. Okay, cool. So if there's no questions, I will continue. Hold on, someone just joined the class. Okay. So now let's just review. I mean, you have linear geometry. We kind of went over this already. What happens if the 3 groups are not identical? Oh, well, this is something worth mentioning. That what if the 3 X's are not the same atom, which in a lot of the cases they won't be. And the answer is it'll be close, but not exact, because the electrons will be kind of pushed in one direction more towards the other, more than the other. So, I mean, it'll be close, but not perfect. So, I mean, it depends. That's the best answer I can give. It really depends on which atoms. So we went and talked about tetrahedral already. So this is what a tetrahedron looks like. So it's kind of like a pyramid with a triangle base. So there's 1, 2, 3. There's 4 triangles that make a 3-dimensional shape. That's a tetrahedron. So if each corner is an atom, so 1, 2, 3, 4, the angles between them are 109.5. So that's why we get that tetrahedral arrangement. So you have methane as a perfect example of that. Then you have trigonal bipyramidal, is which the steric number is 5. And here's the 3-dimensional arrangement of what that looks like. So you see trigonal, well, there's different ways to describe it. So this way, you can kind of think of it as like there's a triangle base and there's a pyramid on one side and a pyramid on the other. But you can also think about it as you have a triangle base and then there's one point of the pyramid on one side, one point on the other. But however you want to do it, it's kind of a weird shape to get your head around. But I mean, now looking at it this way, the best way I would describe it is you have a triangle and then pyramid in one direction, pyramid in the other direction. So not exactly the same thing I said, but still the same concept, same shape. Then you have this trigonal bipyramidal. So here's PCl5. Oh, sorry, that's what I meant. I didn't mean PF5. I meant PCl5. But now I'm sure. I mean, PF5 is still a thing. Okay. And then you have octahedral. So here's what an octahedron looks like. It's kind of like a square pyramid, but there's 2 pyramids. There's one pyramid going up, one pyramid going down. So yeah, it's a cool shape. Octahedron. Okay, cool. So there it is, SF5, perfect example. Now the effect of lone pairs, we talked about that already. So they occupy more space, that's true, but really they have more repulsion. And because they're unbonded, so they have they move faster, they have an electron density. That's another thing. They increase the electron density. And I mean, they're just more reactive. So they increase the repulsiveness of the whole molecule. Okay, so we talked about that already. Now we did all this already. We did everything. We did that already. Did that already. Now we're talking about molecular geometries. We did that already. We did that already. We did that already. See, here's what I meant by the seesaw. So you have the one electron pair that's gonna be pointing up. I don't know what that is. Oh wait, what is that? There's two of them. Oh. I don't know where that came from, but you have the ones gonna be facing up, and then you have kind of your seesaw. If you were to put this on a table, it would kind of be a seesaw. Then you have T-shape. So here's what a T-shape is gonna look like that. You have your two electron pairs. One's going to be facing back. One's going to be facing forward. And then it will push the electrons. It'll push them, or push the bonded pairs, this way, like that. And create a T-shape. T-shape again, linear. So here's what a linear would look like when you have three electron pairs, three non-bonded electron pairs, along with two bonded electron pairs. You're going to have they're going to just push, kind of like we talked about. So it'll push this way and then this way, and then this way and this way. So kind of hold those fluorines in place. Okay, so now here's going over all the octahedrals, square planar. You kind of see how that works. We're going to have an electron pair on the top, here an electron pair on the bottom, like that, and then kind of push the bonds like that. Okay, so here's the same chart again. Here's another chart. So kind of just more summarizing everything. Now, important thing to mention: what if you have a molecule with no central or with multiple central atoms? What you can actually say is you can look at each atom specifically and tell the electron and molecular geometry. So that's I think a question on some of your homeworks is, you given a molecule like this, what is the electron or molecular geometry on oxygen? So we'll do that right now. So for oxygen, the electron geometry, let's count. So electron groups, you have 1, 2, 3, 4. So what does that mean? Who could answer that for me? 4 electron groups, what is the electron geometry?
Tetrahedral.
Good, tetrahedral. Nice, so tetrahedral. Now for the molecular geometry, I put En. Wow, I meant Eg. I'm thinking electronegativity. So for molecular geometry, let's see. You have two lone pairs, and you can think of them as, let's say, one's going one way, one's going the other. Kind of like, here, I'll draw it on the molecule. One's going to be going away from us, one's going to be going towards us, and it'll be pushing this like this. And it says it right here, but it's bent. So it would be bent just like water. So water has So that's what water would look like. And the lone pair electrons would push the bonds down, and the molecular geometry would be bent. For the CH3O, for this molecule, this part of the molecule with the carbon central atom, you can say that it would be a tetrahedral electron geometry and a tetrahedral molecular geometry, because there's no lone pairs. So you'd have group 1, group 2, 3, group 4. And it would be tetrahedral for both. Cool. So look, here's the chart again. Okay, so is there any questions on the shape, on shapes? I'll bring the chart up. Because believe it or not, we're almost done. We just need to go over polarity, and then that's really it for chapter 11. That's going to be on the exam. All right, if there's nothing else, we'll keep going. So polarity. Now, like I mentioned, polarity of molecules is a little bit different than polarity of bonds. Now, for a molecule to be polar, it must have polar bonds, right? Because polar bonds, there's no other way to have polarity than having polar bonds in the first place. And it must have unsymmetrical shape. So unsymmetrical is not a word. It's asymmetrical. It must have asymmetrical shape. So that's the important part that we didn't talk about yet. So here's a very simple molecule like HCl, which we talked about things like it last class, that it has a dipole moment, meaning it basically means it's polar. It has the electrons pulling in the chlorine direction a lot, and the electrons are located in the single bond. And then like basically they would be over here. And it would be a heavily polar molecule. So all of your electron density would be towards the chlorine. But this is a very simple one. And obviously you could see it's a polar bond, and there is asymmetricality. I like that word. I'm not sure if it's a word, but I like it. So then you have molecules that have polar bonds but are not polar. So the CO2, perfect example of that. The carbon-oxygen bond is polar. So, I mean, you're going to have difference, and it's going to be the dipole moment is going to pull more towards the oxygen. But you're going to have two of them. And since we know the molecular shape now, the molecular geometry is going to be linear, then we can say, oh, because it's linear, that means it's symmetrical. Therefore, the molecule as a total or net would have no net dipole moment, and it would be a nonpolar molecule. So we can use our symmetry to figure that out. Now, here's water. So we know the shape of water. Water will not be linear. It will be bent because it has its two lone pair electrons. And you figure that out by determining the Lewis structure. Now, once you know that, you can say, all right, because it is bent, that means it's not symmetrical in every direction. It's symmetrical over the y-axis. It's not symmetrical over the x-axis. And what that means is that your electrons will be pulling more towards the oxygen. So if that's the case, you're going to have a net negative charge, a partial negative charge by the oxygen, partial positive charge by the hydrogen, and you'll have a net result is a polar molecule because you'll have an uneven distribution of electrons. And then your other polar molecules such as ammonia. So ammonia is polar for the same reason that water is. So you're going to have a lone pair of electrons on the top, like it would be like right here. And that would push down the hydrogen bonds. It would be a tetrahedral electron geometry, a trigonal pyramidal molecular geometry, meaning it's a tripod. And because it's a tripod, that makes the bonding asymmetrical. So your hydrogens would be doesn't want their low electronegativity. They don't want electrons. Your nitrogen is going to be the most electronegative. So the net movement of electrons will be towards the nitrogen, making the result a polar molecule. So yeah, from knowing the shapes, you can figure out the polarity. So here's some practice. So decide whether the following molecules are polar. So we'll do this one together. Now, we'll do the first one first. Is oxygen, nitrogen, chlorine. So in terms of, now for polarity, we don't need to focus on electron geometry much. We just need to focus on molecular geometry. Because, molecular geometry is the most important. I'll give you that right now. For our chemistry 1 purposes, we don't really care about electron density and things like that. But for molecular geometry, we need to know in which direction the bonded atoms are facing in order to know the shape and the polarity. So for this case, for our cases, molecular geometry is important, is the most important. Now, for the molecular geometry of this molecule, what would it be? Anybody want to give me a answer? So you have a lone pair up here, and then you would have one, this would be steric number 3, and then you'd have 2 bonds. And you can ignore the fact that one of them is a double bond. And good, Olivia, nice job. So it would be bent. So yeah, another thing is it doesn't matter what type of bonds they are, which I said before for steric number, but in reality, this molecule would look like this. Because remember last class we talked about bond length versus bond strength. So a double bond is stronger than a single bond and the length is shorter. So this wouldn't be exactly symmetrical. It would actually look like that. And that can lead us to our answer. Knowing everything about chemistry, everything that we learned last class and this class, it will point to the fact that this is a polar molecule. One, because it's bent, just like Olivia said. And then two, because the bond lengths are different. And then three, because the atoms are different. So you have an oxygen here and a chlorine here. So it would pull with one strength in this direction. The other strength would be in this direction. The electrons would pull in a different strength, or the atoms would pull with different strength. And also it's not symmetrical. So this is a very polar molecule. So polar for all those reasons. But even if you just knew that it was bent, you can say it's polar. Oh, it turned out nitrogen and chlorine have the same electronegativity. So this is going to be a very, very weak pulling. Really in no direction. It would just be... Now, okay. Remember I said last class where even if the numbers are exactly the same, there still is a little bit of polarity because the atoms are different. The elements are different. That's true, but it would be like a very, very slight nothing, almost nothing. So everything would be pushed more towards the oxygen. Okay, next one. So the molecular geometry for SO3, molecular geometry. Anybody want to answer that one for me?
Is that just trigonal?
Yes, so trigonal planar, correct.
Planar.
So yeah, so there's going to be trigonal planar. Good. So trigonal planar means that all these angles are going to be 120, even though the picture doesn't show it. They're going to be 120. And also, they're all oxygen, and sulfur's in the middle. So that means you're going to have an equal pull in every direction. Oh, well, why did I choose red again? Here. You'll have an equal pull in every direction almost, and you will have a basically non-polar molecule. Now, that some of you may be thinking, doesn't that kind of go against what I just said, where when I just draw an N? So here we go. So that kind of goes against what I said about bond length being a factor. It is a factor, but I mean, in this case, it's going to be very small because all the atoms are the same. So it's going to be, it would look like this. It would kind of push with like a couple % more towards this oxygen, but these ones would be a different, it would be very, very close to symmetrical in terms of single bond versus double bond. Very close. So we can basically say that this is non-polar.
I have a quick question.
Yes.
So can you reiterate how you went from the shapes to polar and non-polar?
Yes, because the shapes tell us the symmetry.
Mm-hmm.
If there is perfect symmetry, which there is in this SO3 molecule, and the atoms are the same, meaning oxygen, 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 the bonds are the same, then it will be non-polar. Even though a singular sulfur-oxygen bond is polar, the fact that the whole entire molecule is symmetrical, the electrons will pull in equal and opposite directions, making it non-polar. So basically, the molecular geometry tells you if it's symmetrical. If it is symmetrical, it's non-polar. That's all the time. If it's asymmetrical, you have to be like, okay, is the bond itself polar? So let's say, let me do an example. Here, we'll do this. Let's say if this molecule. I'm not, the dots aren't in there yet, but not the point. So let's say if it's bent, right? You have 2 nitrogens and nitrogen chlorine. Now, this molecule, even though it is bent, and that asymmetricality tells you, oh, it's probably polar, you have to look at the bonds. So nitrogen-nitrogen bond is nonpolar because they're the same atom, same element. Nitrogen-chlorine bond is still nonpolar because look at the electronegativity numbers. They're the same. So this molecule would be nonpolar, even though it's bent. So the molecular geometry tells you symmetrical. If it's symmetrical or not symmetrical, you still have to look at the elements involved in the bonding. Then the difference in electronegativity of those elements and the information of the molecular geometry and the symmetry will help you figure out if it's polar or non-polar. Does that make sense?
Are we going to be given the electronegativities, or are there going to be examples where we have to calculate that on our own too?
Good question. So you're never going to need to calculate the numbers. If, let's say there's a question like this, the required numbers for that question will be given to you. The only thing that's important about electronegativity to know is the trend, that it basically increases going up to the right.
Right. Okay.
Right. So if you were given like HF or really anything with fluorine is pretty polar. So it would be apparent. You wouldn't be given weird ones like nitrogen and chlorine. So, and if you are, you'll be given the numbers. Okay, cool. All right, so we have polar, non-polar. Good. So we're basically done. Now, what you can do now on the homework, there are questions. There may be like 1 or 2 questions involving the hybridization, but hybridization is so easy. So easy, a caveman could do it. But here is hybridization in a nutshell. Basically, you can go off what hybridization is sometimes the electrons like to create hybridized orbitals, which means they kind of mix. They kind of like they jump orbitals because electrons are moving very fast. There's a lot of energy involved. So basically, they like to jump. And when they do, there could be different hybridized orbitals that they make. And basically, the hybridization can be described of every molecule depending on its molecular geometry. So, or depending on its electron geometry. So if you have 2 electron groups attached to a central atom, we call it sp hybridized. If you have 3 electron groups attached to an atom, it's called sp2 hybridized. If you have 4 electron groups, it's called sp3 hybridized. So what that means is sp1, 2, and 3, this means it would be the hybridization would only occur between the s orbital and then the p subshell that's like, let's say x. There's 3 subshells for p. It'd be like p1, p2, and p3. There'd be px, py, and pz. So maybe you saw that in the slides, but that's not really too important. The idea is that when you're adding more electron groups, they will fill more p shells. So the next one would be s. It would be px, py. So you could call it sp2 hybridized. The third one with 4 electron groups would be s, px, py, pz, or what we call as sp3. 5 electron groups, that's when you introduce a d orbital. So it'd be called d, dxy. So it'd be called dxy, s, px, py, pz. And then the last one with 6 electron groups is dxy, xz is one of them. And it goes further beyond this, but it's not really too important. Py, pz. So the idea here, if you want to really simplify it, is that if you put an exponent 1 next to the s, you count up all the exponents, and that equals the number of electron groups. So sp3, s1, p3, 4 electron groups. D sp3, d1, s1, p3. So 1, 2, 3, 4, 5. 5 electron groups. D2, sp3. 1, 2, 3 for the S, and then 3 more for the P, so that's going to be 6 total. And you have 6 electron groups. So that's basically it. You can determine from just one molecule the polarity, the molecular geometry, electron geometry, and the hybridization state based on this little chart. So yeah, that's basically it. So here's an example of that. So yeah, is there any questions on anything? So the test will be Monday. So Monday, 9 o'clock. I'll be in the Zoom room probably around 8:30, and so you can ask questions then. I'm gonna pull up Moodle. Where's Moodle? Moodle. There's Moodle. Okay, so Moodle. Here we go. So here's fall 2017 and fall 2018 exams with the answers. And oh, look, a common exam 3 study guide. Cool. I don't remember making that. Let me see. Oh, cool. Maybe I didn't make it. Yeah, I don't think I made this, but I have it. So use the Rydberg equation. No, we didn't learn that. All right, this has to be modified. Yeah, this is maybe from 2016. This is from a long time ago. Oh, we did this. This is with the N. This is with the they just call it the Rydberg equation. I didn't even know it was called that, honestly. But because I never use it for anything. But yeah, we covered most of this stuff. Okay, so I will go over this in a separate video and post it on YouTube. Also, I didn't post the chapter 10 video yet, and I'll do that. I'm gonna end the recording now. So stop recording.